So it's an absolute pleasure in the AKT colloquium today to have Professor Fred Chong. He is the Seymour Goodman Professor in the Department of Computer Science at the University of Chicago. Fred also leads up the EPIC project. It's a fantastic acronym. We're running out of quantum acronyms, Fred, so we need to write some code to find more of them.
Oh,
And this is an NSF Expedition Center in Computing. Fred has numerous awards coming from various agencies and has also been in various universities throughout his career. So it is an absolute pleasure to have Fred to talk about various topics in optimizing performance of near-term and noisy quantum computers. So thank you, Fred.
great. Thanks so much. Be here. Let me share my slides. All right. So as Erfan mentioned, I lead this project called EPIC, and a lot of what I'll talk about is work that we've done with my great collaborators at MIT, Princeton, Duke, and Santa Barbara. And what I'm really going to focus on today is, a great advantage I think that we can get from full stack optimization of our software, which we want to be perhaps more physics aware than we're used to, at least for us who come from the classical computing side. And so, what I'm going to talk about is how to strategically break abstractions in our software stack and give you examples of where we could get just enormously greater efficiencies by doing this. So I imagine that most of the people here are probably somewhat associated with quantum computation, but for those of you who are not, and I'll just give you also my view on, as a computer scientist and computer architect, why quantum computation is so exciting. And as an architect, it's really exciting because it's really the only technology that we know that can potentially scale computation exponentially with the number of devices we put into a machine. And that really will give us potentially the ability to solve intractable problems in chemistry, simulation, and optimization. And as an architect, it also is an exciting technology because it gives us another sort of exponential scaling curve, or even double exponential scaling curve to play with, albeit for specific domains. And also, just studying quantum computation has led to interesting insights in classical computation, already in chemistry, physics, and cryptography, and who knows what the future will hold. Now, why are we so excited now? Why do we have the National Quantum Initiative, and why are so many scientists getting into this area? Well, I think the biggest excitement is that we finally have, having been in this field for a while, some non-trivial machines out there, right? And these machines are really exciting, but they're really noisy, right? And so John Prisco coined this nice term NISQ, speaking of quantum acronyms, which I like because it sounds like risk. But we're really at this privileged time in history, as he says, because we're at a point where we have machines that are really too big to simulate. And really, there's going to be new science done because we can study these machines, and hopefully they will help us compute something and solve useful problems. Now, even though we're in this really exciting time, there is a pretty significant gap between the machines that we expect to have in the near future and what we want to do, right? And so what I have plotted here is the number of physical qubits in these machines on a log scale versus the average 2-qubit gate fidelity on these machines, also in a log scale, right? And you can see that the machines over time have made great progress, right? Through material science and through physics and experimental methodology, we're getting machines that are moving exponentially up from the lower left to the upper right, right? But it's also the case that there's a significant gap between these machines and where we want to be with the algorithms we want to run. And what our project was created with this goal of what we call the EPIC goal, right? So we want to develop algorithms, software, and hardware in a sort of a co-designed way that will close the gap between algorithms and devices by a very large factor. Our goal was 100 to 1000x. And if we really got 1000x, that would be 10 to 20 years of hardware development, right? And so we really hope to help bring algorithms closer to machines by making these algorithms much more efficient through software optimization. And it sounds like an ambitious goal, but actually, it turns out that we can find many techniques to make this, to try to attain this goal. And in fact, so our project is a 5-year project. We're halfway through. And we found, in fact, many optimizations, each about 2 to 10x, and even some up to 10,000x, which actually sort of exceeds our goal in some ways. And in those 2.5 years, with these optimizations, we've put out about a little over 60 papers, 4 of which won Best Paper, 6 patents, 1 startup has just been spun out. And then we also have pretty substantial education and outreach efforts. We have a textbook, and also we have a fairly nice sort of tech transfer into industry, where many of the techniques I'll talk about today have already been integrated into open source software such as IBM's Qiskit and Google Circ. Okay, so this is a quick summary of some of the things that we've done in the last 2.5 years. And what's interesting to look at in this big table is on the right, the kinds of efficiencies that we're able to get through this kind of physics-aware cross-layer optimization on the stack. And then also, you can see at the bottom, we have a whole bunch of education efforts also to really promote this view of system design and software optimization for quantum systems. Now, what I'm going to do today is I'm going to give you a quick view of 6 of these things. And the idea is to give you an idea of how we do this, right? Like, what kinds of optimizations can you do when you try to connect the algorithms and the compiler and the devices together. All right, so let's get started. Now, the first one I'm going to talk about is some work we did back in 2019. And with our Princeton collaborators, Chicago and Princeton. And in that work, what we're going to do is we're going to adapt our software to the daily variation of IBM's superconducting machines, and also actually later Rigetti and the Maryland trapped ion machines. And this work has had some pretty good impact. In fact, it's really changed the way that most programs are compiled on quantum machines. It's been integrated into IBM software, and it received this thing called Top Picks, which is given to about a dozen papers every year in all of classical and quantum computer architecture. All right, so the problem we want to look at is hardware variation. Many of you may be aware that hardware such as IBM's hardware varies significantly day to day. And IBM publishes their calibration data every day for their machines. And if we take a look, so here on the top right, you can see that various qubits, here denoted in the different colors, Q0 through Q13, they vary on the y-axis. We have a measure of the quality of the qubit, and that essentially, you can see that varies significantly from day to day on the x-axis. And it's not even the same qubit that's the worst qubit every day, right? And then if you look at doing gates or operations between different qubits, here we have operations between 3 different qubits. That also varies significantly day to day. And here we have plotted the error rate versus the each day. And once again, it's not even the same pair that's the worst every day. So the idea is, we can build our software to target a specific machine for a specific day. And this is really very different from the classical view of compilers, right? So if you deal with a classical compiler, it's going to compile for a specific machine family, and you'll get a binary that can run on any machine of that family on any day, right? So this really breaks the model of what we would normally do. Now, the idea is really simple, right? So here on the left, I have a simple quantum circuit. If you're not familiar with these, the qubits go in on the left, time goes from left to right. The little meters on the right are the results, where we measure the result, and the The boxes in the middle are single qubit gates or operators on a single qubit. And the little dots with the pluses, those are 2 qubit gates. They're controlled NOT gates. All right, so if you take IBM software and you map it to a machine, one of their machines, you'll get the thing on the upper right? So on the upper right, you can see the P0 through P3 qubits are mapped to different dots, which represent qubits. And what you see is what the IBM machine tries to do is it tries to keep those qubits close together. But it's not aware of the fact that you might have qubits that aren't so good. And here we've drawn those in as gray circles. And you might have some links between qubits where doing an operation between those 2 qubits is not so good. And we show those with those red X's. So instead, we actually use a solver, an optimizer, to follow the bottom path, right? And on the bottom path, you can see that we still keep those qubits together when we map them onto the machine, but we try to avoid the red X's and the gray circles, right? And so the key is to encode our constraints in such a way and balance the goals of the optimizer. So we get low communication cost of keeping the qubits together, close together, and avoid the bad qubits and the bad links. And here's the result, right? So if we run this on a number of different quantum circuits on, in this case, a 14 qubit quantum machine back in 2019, what you see is if you compare the native IBM software, which is the darkest bar where it says Qiskit, and here higher is better, right? It's a success rate of the application. You'll see that the dark bar, sometimes you can't even see it because the reliability is so poor. And then if we take our software and optimize for communication, we get the orange bar. And then if we take the solver and optimize for communication and trying to avoid bad devices, bad couplers, you get the green bar, right? So in general, we get about a 3x on average improvement over the IBM software, up to about 28x improvement in reliability. And as I said, this has been quite successful. It's now been integrated into IBM Qiskit. So in fact, this is how most compilers do their compilation now. It's also been integrated, I believe, into the Maryland tool suite and the Rigetti tool suite. And once again, the key was to break this abstraction of, we only compile once for a particular machine family. We're going to do a very tailored compilation. All right, so let's go a little further, right? So now we're going to break the abstraction of compiling software to a set of instructions or gates. And instead, we're going to compile our programs directly to pulses, right? And this work has evolved a fair bit from our initial result where we took functions and compiled them to actually something which has to do with what we call partial compilation. And I'll show you that. But the idea is simple, right? Once again, we take a part of a quantum circuit here on the left. And the standard path for compilation is we take that circuit and we compile it to a number of primitive quantum gates, or what we might call quantum assembly. And then we take each of those and we compile those to pulses, right? And so these pulses here on the right are for Dave Schuster's cavity machine. But what you see is a fairly complex series of pulses to implement that function. But what we find is if instead we treat this little circuit as an input-output function, and we feed it to an optimizer, in this case, the GRAPE gradient ascent optimizer, we can go directly to a pulse implementation, which is significantly simpler and shorter on the bottom right. And the result is we get a pulse sequence is about 2 to 10x faster. And the idea is that if you think of this as an initial state to a target state, here I've shown on a sphere, right? When we compile instruction by instruction, we have this fairly indirect path, which is shown by the gray arrows. But instead, when we use the optimizer, which incidentally is very expensive, we get a more direct path. Now, one of the problems that we discovered was it can take hours to compile a program before we can run it. And this is particularly a problem for iterative algorithms, and in particular hybrid algorithms such as variational algorithms, which would require you to recompile thousands or even millions of times. And so, if we look at a variational algorithm, right, for those of you who aren't familiar with them, it's a cooperative algorithm where a classical algorithm uses a quantum kernel and loops thousands of times or even millions of times and repeatedly calls that quantum kernel, right? In this case, if we're looking at the variational quantum eigensolver, we're trying to solve a quantum chemistry problem. And what you see is that certain parameters will change every iteration. In this case, these different thetas, rotations on these different qubits. And so what we want to avoid is spending hours of time to recompile each of our iterations as we go. And the technique we developed is based upon fairly established classical technique, which is partial compilation, right? So we are going to take advantage of previous compilations to speed up a compilation where only a little bit has changed, right? So we can break our, in this case, our variational quantum eigensolver into pieces where only one parameter changes here, which are these thetas. And then we recompile those pieces every iteration, but we take advantage of previous compilations of those pieces. And so what we find is we get, for these programs, about a 2x speed up in terms of the actual pulse sequence, but about a 10 to 80x faster compilation time than previous methods. And so the key was really to break that gate abstraction and target pulses, and then also be aware that we had to do essentially some runtime or partial compilation. All right, feel free to stop me with questions if you like. Okay, so now let's take a little look at what we can do at the application level. This is something we did for VQE, or the Variational Quantum Eigensolver in particular. And what we find is that there is a significant cost in all these iterations to actually do the number of measurements that's required to estimate all the terms in the problem that you're trying to solve. And what we do is we actually restructure the algorithm to get 10x, actually 30x more out of each measurement. So what we find is that the measurements aren't independent. Okay, so the idea is, here is a set of terms that you have to measure in each iteration in an example. And it turns out that you don't have to measure every one, because since they're not independent, you can actually do a little pre-processing, measure a whole bunch of them together, and then post-processing and separate those terms out. And in fact, there was a method proposed called qubit-wise commutivity, which uses a commutivity property per qubit to give you groups. And here you can see, you can break the system up into groups where all the blue terms can be measured simultaneously. And then there are 4 more terms that have to be measured separately. And it turns out that if we developed a method called, which we use general commutivity, which gives us, in this case, just 2 groups to measure. And we find that if we look at a number of different problems, which are represented by the input molecule that you're trying to estimate the ground state of here, you can see that the blue bar is how many terms you would have to measure without any of these techniques. The orange bar is this previous qubit-wise commutivity, and the green bar is our technique. And we, in fact, finding commuting groups is a hard problem, so we use heuristics. And so here are a number of heuristics that we tried that basically reduce the number of terms that we have to measure, and where higher is better here. So in the end, what we find is that we can significantly reduce the number of terms measured. And here's actually a simple experiment that we ran on an IBM machine. And you can see that our approach, which is which are the blue squares, are closer to the ideal predicted line than the unpartitioned, or so the previous approach, which takes more measurements. And in this case, what's happening here is we get about 10% better accuracy through making better use of the number of trials that we have on the machine. But then finally, there is an interesting effect here, which is that there's actually potentially some advantage in having redundant information in your measurements. And so you actually don't always get a higher fidelity answer if you take fewer measurements. And what you have to worry about is you want to minimize the covariance between the different groups that we measure. And so we actually have an algorithm that does that, so that we get both small number of measurements and a high fidelity result. All right. So I like that example because it's one of the examples where, by actually looking at the algorithm level, we're able to do something that really increases the efficiency of the software stack. But let's go back to sort of the compiler level. So in our fourth example, what we're going to look at is how to make better use of our qubits. And what we're going to do is we're going to try to reuse some of our qubits for different parts of our computation, in particular Ancilla qubits. And this is an interesting problem because it's similar to managing your memory on a classical computer, or something we might call garbage collection, which is essentially reclaiming the memory that you're not using anymore. But a very interesting and significant cost here is that we have to do uncomputation, right? So we actually have to remove the relationship between a qubit that's no longer used and the result of that we carry forward in our computation. And that means that we have to invest operations or gates in doing this uncomputation to get back our qubits or our memory. So there's what we might call a space-time trade-off here, right? And so another interesting problem that we have is that some of our functions might be nested. Okay, and so if we take a look on this, on the left here, I have another quantum circuit, but in this case, what I have is a unitary nested in another function or unitary. So this U of F is a nested computation inside of U of G, right? So what does that mean? Well, the obvious way, or sort of simple way that we can do this is we can take that box U of G with U of F in it, and we can do its sort of mirror image or uncompute on the right. And what that does is that gives us back those blue circles on the right, right? So the blue circles come in on the left, those are Ancilla qubits, and then they're being used. And once we uncompute, then we can get them back and use them again. Now, what's interesting is if you look at the top example, we can actually be more aggressive and uncompute U of F early, right? And what that does is it gives us back this middle qubit. You see those blue circles in the middle at the top, and we get that back where we would not have gotten that back down in the bottom approach, right? And so by being more aggressive, we can get qubits back earlier, and then we can use them for something else in some other part of our computation. But we pay pretty significant costs because not only do we have to uncompute U of F, that it turns out when we have to uncompute U of G on the right, we have to recompute U of F, right? So it's a sort of interesting effect that we have of recomputing our uncomputed things. So it's a lot of extra gates. Now, what's surprising is, so we can take these, we basically have three options, actually four options. We can actually not uncompute anything and use a lot of qubits. We can be lazy, which is the bottom path here, and only uncompute sort of a minimal amount. We can be eager or aggressive and uncompute in the top as often as possible. Or actually we can have some combination of eager and lazy, which this is a hybrid method, which not surprisingly turns out to be the best. And so we can compare these. So here, lower is better. We're basically measuring error rate. We look at a number of quantum circuits and we compare lazy, eager with the hybrid method, which we call square, okay? And you can see that the hybrid method ends up being generally better. In some cases, doing too much uncomputation could be a really bad thing. But what's surprising actually is that this approach, we actually designed this approach for future fault-tolerant machines in which gates would not be so expensive. But we were surprised that when we ran this on an IBM-like machine here, this is actually simulated. It's an IBM machine, but with parameters that are slightly better than current IBM machines, because you don't see this uncompute effect until you have deeper circuits. But what we found was doing uncomputation actually can improve fidelity on NISQ machines by 50%. Okay, and that actually was quite surprising to us, right? Because we didn't think that using gates to do uncomputation would save us that much, right, on NISQ machines. But it turns out that it can be cheaper to invest gates in uncomputation and get a qubit to use than to move a qubit from far away, which is what ends up happening in some of these machines. So here on the right, I have a picture of an IBM machine. And let's say that we needed a qubit for our computation at position 24 here, right? So we can either uncompute at 24, or we can, say in this case, move a qubit that's free or hasn't been used from position 50 over to 24. But these red arrows represent swaps, which cost us gates, and those gates reduce the fidelity of the computation, right? And so what was surprising was that uncompute, if you're strategic about it, can be fewer gates than communication. And that ended up giving us about 50%. And then we actually find that this approach would be much more effective even when we have future larger machines and fault-tolerant machines. All right, so that's a view of another sort of classical technique of memory management and really mapping and scheduling and how that affects NISQ machines. Now let's take a look at some of our work, which really breaks the abstraction of binary computation, right? So what we're going to look at here is computing and representing information with 3 states instead of 2. And this work has also been fairly popular amongst actually different experimental platforms, because this is a way to get sort of more out of your devices. But there are subtleties and problems, which you'll see that we avoid in a certain way. Now, the idea of ternary logic and computing with 3 states is not old at all, or it's not new at all, right? Ternary logic, in the classical world, has been around for some time, but really hasn't caught on, right? And part of that is because in the classical case, you have essentially a finite amount of signal, right? So if you are representing a bit, a classical bit, using voltage levels from say 0 volts to 5 volts, typically you break that into 2 pieces with a noise margin. But if you want to compute a trit or a 3-level bit, then you have to break that up into 3 pieces, and basically you have less signal and less noise margin, right? So you still have the same range. Now, qubits and qtrits and qdits are interesting because, for example, if you look at a superconducting qubit you have a lot of energy levels. And we engineer the system so we typically use the lowest two energy levels to represent a qubit, but we could use one more level to represent a qtrit. Now, of course, going up to the third state exposes you to more error, and that's something we're going to have to model. And also, measuring qtrits and qdits is hard. But it turns out we produce a construction which is qubit in to our circuit, qubit out from our circuit, and only qtrits in the middle. So it sort of avoids this state discrimination problem of measuring qtrits. All right, so a particular gate that we're going to look at here is what we call the generalized Toffoli. And so it's a multi-controlled gate where the qubits at the top here control whether the target at the bottom gets the operation performed on it. So essentially you have to perform a logical AND on the top qubits here, right? And there are a few ways we can do that. If we don't have any extra qubits, or Ancilla as in the last work in memory reuse, then we have to do it linearly, right? So for n controls, it will take n steps for us to combine each of these two at a time to figure out whether we should do the operation on the bottom. Now, we can also do this a lot faster. In parallel, we can build a tree. And so then for n controls, it will take log n time. But in order to build the tree, we will need n ancilla. So we need essentially twice as many qubits to be able to do this faster. Right? So we're going to do this with qtrits. And we're going to build this log tree. But instead of having extra qubits to build the tree with, we're going to sort of save ourselves a factor of 2 in devices by taking advantage of the third state in our actual data qubits, right? And now, one thing to consider is if we had Q-quartz or 4-state devices, then that would just be 2 qubits in one device, and it would be trivial to do this. It's just a little more subtle here when we just use one extra state. And the way we do that is with these special operators here. These are controlled modular X gates. So they're mod 2, or I guess mod 3. And the ones and twos in the circles are the control values that cause those gates to occur, right? And you can see that we can build a logarithmic tree structure, and you can see the mirrored structure because you have to uncompute whenever you do an operation like this, okay? So what we get is a logarithmic depth, and still a linear gate count, but it's a factor of 2 better, right? Okay, so the advantage here is if you compare our approach to the base case, which is qubits with no ancilla, or qubits with 1 ancilla, which makes it a little more efficient. You can use, basically with the same number of devices as the blue line, the orange line gives you an asymptotic depth advantage, right? So you're depending upon the number of controls on the x-axis, you can get a log advantage in the depth of your circuit. Right? Now, asymptotically, the Qtrit implementation has the same number of same growth in gates. It's still linear as the qubit and qubit plus ancilla versions on the right here, but it has a much better constant factor. Right? So it has a great advantage in terms of both gate count and circuit depth for basically the same number of devices in your machine. Now, one of the problems that we have is when we go into the third state, there's more noise, right? And so the trade-off is you're exposing your system to more noise using the third state, but you have significantly better fidelity through lower circuit depth, right? So you're making your circuit shorter. So some of the operations, each gate might cost you a little bit more in terms of error, but you have many fewer gates. Right? So here we've modeled on the left the IBM machine using current parameters, which is the SC category on the left. And we look at the fidelity of a generalized Toffoli gate in the same three options: the base case, which is qubits with no ancilla, which is blue. The hashed gray bars are qubit plus one ancilla, and orange is our Qtrit option, right? You can see that the Qtrits have much better fidelity because the circuit depth is so much better. Now, as we make things better, so SC plus T1 is basically making T1 time 10x better, so making the qubits 10x better. We see that the difference is smaller, right? And then as we go forward, so SC plus gates is making gates 10x better, and then SC plus T1 plus gates is making both gates and T1 time 10x better, right? But it is still the case that we get a significant advantage, especially over the blue bar, because of lower circuit depth. On the right, we ran some models for trapped ion machines, both a orange bar in the middle, which is a sort of more straightforward three-state implementation of Qtrits, and then a four-state, somewhat error-mitigated version in the dressed Qtrit. And you can see that, once again, comparing blue and gray to the orange bars do better. The difference is smaller because, of course, the current trapped ion gate fidelities are better than the current transmon ones. Okay, so the end result is essentially it can be worthwhile to look at Qtrits, even though they can give you more noise, because of the advantage they can give you in terms of your end circuit that you get. Right? And in fact, that's up to about 70x reduction in ancilla, depending upon how big your controlled operators are. Like I said, this has been fairly interesting as a model to implement on different experimental platforms. And in fact, we have recently just done this, some Qtrit experiments on IBM machines using their open pulse interface. It's a little tricky because the waveform generators are limited to not go into a frequency that would allow you to go from the 1 to the 2 state. So we have to do some sideband modulation, but the fundamental technology allows you, of course, to get to these different states. And so we're able to do, in this case, a simple 3-state counter using a single device. Okay, so one last example. So the last example I want to talk about is it's interesting because it illustrates the interaction between sort of hardware design, architectural design, and software optimization. And in fact, what we're going to do here is we're going to try to mitigate crosstalk using tunable qubits, but not tunable couplers. And we're going to find that we can achieve a similar result to a machine that has tunable qubits and tunable couplers. Right? So for those of you who aren't familiar, with the crosstalk problem is most significant if you try to run two 2-qubit gates that are near each other, or in fact, sort of connected to each other in the topology. So in this case, the two black boxes here represent a 2-qubit gate between 1 and 2 and 6 and 7. And they experience significant crosstalk because 1 and 6 are coupled together, right? And it turns out the error rate on an IBM machine increases by about 10x on those 2-qubit gates if there's crosstalk. So what we're going to do is we're going to look at this space of machines, right? So these are different design options for different machines. And so what we're going to focus on is a machine that has a tunable qubit and a fixed coupler between each qubit. And that's a little bit like the Rigetti machine. And if you compare that versus an IBM-like machine, which has fixed qubits and fixed couplers, we're going to find that we can get about 13x better fidelity on our machine by reducing crosstalk but our machine is arguably harder to build, right? Because it has tunable qubits and the IBM machine does not. But we also find that our software techniques, coupled with this machine model on the left, on the top left, can perform about equivalently well to a machine like Google's Sycamore machine with both tunable qubits and tunable couplers. And that machine is arguably harder to build than one with fixed couplers, right? So essentially we're arguing that if you compile in a application-aware, crosstalk-aware way, you may not need tunable couplers. And how do we do this? Well, we basically have two phases in our compiler where we take the connectivity graph of the machine and we do a simple graph coloring that assigns frequencies to that machine in such a way that the idle frequency, or we call what we might think of as the parking frequency of each qubit, is not the same for neighboring qubits in the graph. And then we construct what we call a crosstalk graph, which is basically different 2-qubit operators that can be near each other or connected to each other in the machine. And then we color that graph in a way such that we can assign frequencies such that neighboring 2-qubit gates will have different frequencies. Now we do this actually on an application basis and a time step basis, right? So for each application and for any given time, all the gates that can be in parallel are assigned to, we create a small crosstalk graph and we color that one. So essentially we're always working with relatively small graphs per time step. And the result of our approach is for a number of different small circuits. If we compare the blue bar, which is the IBM-like fixed frequency machine, so fixed qubits and fixed couplers, versus our sort of best approach, which is the red bar, you can see the red bar is always significantly better than the blue bar, where higher is better in this graph. And then you can see that the blue bar is generally comparable to the green bar, which is the Google-like machine, which can use fixed couplers or use tunable couplers, right? Now, the difference is, of course, you can use a tunable coupler to break the crosstalk effect between two different gates. But what you can see here is through sort of clever frequency assignment and scheduling, we can avoid that crosstalk without having to build fixed couplers, right? Or tunable couplers. Where building a tunable coupler is basically equivalent to building, another qubit, right, in your machine. Okay, so let me take a step back and wrap up, right? Our view of this sort of full stack physics-aware software design is what we might think of as a sort of an overall sort of arching sort of system view, or what we might call quantum computer systems design. And what we're really doing is we're building a domain-specific software stack from the program level all the way down to the hardware level. And that's how we did this crosstalk mitigation work. And in fact, it's how we did all the examples that I showed you today, except maybe as the measurement one for at the application level. But in general, we're looking at building a very specific optimized software stack for each machine and potentially for different applications. This trend is analogous to a very popular trend in classical computer systems right now. So our vertically integrated stack is analogous to integrated domain-specific stacks such as TensorFlow, right, for machine learning in the classical world. And this was really viewed, there's a view that this is a bit of a revolution in computer systems and computer architecture. And it was mentioned in Hennessy and Patterson's Turing Award lecture a couple of years ago. All right, so let me just give you one slide, which I'm not going to have too much time to talk about. But another big problem that we worry about is program correctness and verification, right? And we're really going to have this bootstrapping problem, right? Which I have this picture of the forklift on the forklift, right? So, we're going to have machines where we're really pushing the boundaries of their reliability to scale them and to build, workable quantum hardware. And we're going to have software that's really not tested at the scale of those machines, since the computational power of those machines grows exponentially. And so we're going to be in this situation where we really want to develop methods to test our software and to verify that it's correct. And there's been some interesting work recently on sort of testing in quantum assertions, but even more interesting, I think, is formal methods for proving that our software is correct. And in fact, we use some formal methods in this last work called Certique on the IBM compiler. And we're able to actually find 3 bugs in their compiler based upon our formal verification framework, which uses an SMT solver. And then finally, there is this very fundamental question, can we, in sort of tractable time, check the correctness of quantum programs that have quantum advantage, right? So and the fundamental nature of this is if we require something that's reducible to the answer of that program to check it, and we can do that in polynomial time, we've basically proven that it has no quantum advantage, right? And so, the fundamental thing is, if there is quantum advantage, is there some property we can check that it's not too close to the answer that tells us something about whether the program is correct, right? And so I think this is a really exciting area. I'm not going to talk too much more about it today, but I just wanted to mention it. So I'm going to skip a few things about correctness, and I'm going to sum up. So, I talked about this gap between machines and algorithms, right? Another interesting thing is, is there a gap between what we learn today about building software and systems for a small number of qubits and noisy machines, and what we expect long-term, right? Basically, the things that I talked about today, how many of those will persist once we get to much larger machines or fault-tolerant machines? And it's interesting because I actually started my work 20 years ago on the right side of this before we had any machines. And, and lately we've been on the left side of this. But I would say that my intuition is a lot of what we learn about sort of physics-aware software stacks will persist into the future, because it would be hard to imagine actually a time when qubits are, perfectly reliable and essentially free in terms as we are in the classical world, right, for bits. Although even in the classical world, we're backsliding a bit as things have scaled and we have hardware variation, right? So even classical hardware, classical software is becoming more aware of the physical properties of those systems. So I think that many of the things that we learn about how to strategically break abstractions and expose physics to our software stacks and our algorithms will persist into the future. And so let me just end where I think that this computer systems view, right, this full stack view of designing quantum systems is really critical. We wrote a book about it, actually, and developing an edX class about it. And we really hope to sort of advance this, this view and this discipline, and build a workforce that of computer scientists and systems people that can think more about the physics of these machines. And you can find out more about, a lot of things I talked about today went by really fast, but we have our EPIC project. We have a website which is quite extensive and has many of these materials and even code and different infrastructure to look into these things. Thank you very much.
Thank you, Fred, for the great talk. Let's clap for our speaker. We've gotten good at this, Fred. So we have the real clapping, the emoji clapping. Great. So the floor is open for questions from the audience.
Well, I have a, well, it's not really a question. Fred, can you please go back to the graduate slide?
Which one?
I don't know, a couple of slides back. You had a slide with pictures and uh, soon to be graduate, soon to graduate students.
Oh, graduates.
Yeah.
Oh, yeah. Okay. That's actually the last slide. Yeah.
All right. Okay. So if they are not spoken or they could be interested, send them our way, please.
Yep. Yep.
I give a chance. Okay. All right.
These I have actually more graduates in these. These are the ones that are the most interested in academic jobs, but and also lab jobs potentially. Um, and the two bottom ones are actually postdocs that joined recently,
Okay.
and the two top ones are yeah are grad students of mine that are graduating. And yeah, they're all excellent.
So Fred, maybe I can ask one question about, you talked about, in these machines that have variations of T1 or gate fidelity or other things which can vary on all sorts of time scales, whether it's hours or days or what have you.
Yeah.
One of the things that we're also looking at the moment are sort of noise characterization methods that reveal some very subtle noises. And in particular, trying to use machine learning methods to try to figure out what the actual underlying noise model is. That goes a little bit beyond some average metric of what's happening in the qubit. There are things, for example, certain noises that are caused by interactions on another qubit, right? And those things are a little bit harder to unravel. So is there a way that as we get more sophisticated in terms of our noise modeling and our noise extraction, that we can plug into these kind of more aware compilers that you were talking about?
Yeah, absolutely. I mean, for example, the mapper and the scheduler right now just takes in the calibration from that day, right? And that calibration data is pretty stale by the time that we run it. And
Right.
you put your thing into the queue, and I mean, there are some we are actually just working on maybe redesigning or suggesting some redesigns for the way the queues work, right? Because right now you compile your program using this morning's calibration data. And in fact, I think they actually calibrate more than like twice a day, but they only publish once a day on those machines. But you might cross the calibration boundary and have your program compiled for the old data, right?
Right.
But in your case, if you had actually like a more realistic sort of real-time model of how what the machine state would be when we run this, uh, the program. Now, either if we could predict when the program is going to run, we could use the model to tell us what to compile for, or we could compile right before we run it, right?
Right.
If the queue allows us to do that or something like that.
Uh-huh.
But yeah, we would love to have such a model. And it's also the case that, that's just the simplest technique that we use, right? Like, for example, we also compile in like different error mitigation methods, and it would be useful to know how the machine is drifting, over time. And once again, the queue is a bit of a problem because we don't actually know when we're going to run a lot of times. But we also run sometimes a dedicated mode without the queue, and then we, based upon the last calibration data and whatever machine learning model we have, we could predict, right, at a particular time what noise we're going to see. And we can do all kinds of things to either schedule or map around the noise, or we could insert extra pulses to try to compensate for some of the things.
Yeah, I think that'd be tremendously interesting. And I see Akil Hashim sort of turning on his camera. I mean, as we run cycle benchmarking of errors, this has been, I think, tremendously illuminating in terms of what are all these subtle things that can happen. And we
Yeah.
can certainly run that. I think, well, we are controlling the queue on our machines, so we can sort of run that in whatever sequence we want. And I was just curious if that, if that can be plugged in somehow to the optimizer, we may find great benefit from that.
Absolutely. And also, even just at a more fundamental level, the IBM systems that are right now our most accessible systems, but they're also poorly understood. And so a lot of times we'll come up with some sort of error mitigation technique, and it just doesn't work because there's all this other noise happening that we don't know about. And so just understanding what the noise is, right, would be a huge benefit to us, so that we know, right, you know, whatever particular thing we're doing, what it's addressing, and then what's not being addressed, and whether we have to come up with something else, or whether we at least can isolate it so we can measure what's going on. We often have techniques that work in simulation using IBM simulators, but then we actually run on the machine doesn't work or it doesn't behave the way you expect because there are like 100 other things going on, right? And
Right,
so,
right. In fact, I mean, there's a hierarchy of errors that one has, right? So, for example, we have these idle errors, right, that can be sort of understood due to some kind of crosstalk that's there, either classical or quantum.
yeah,
There are other drifts in time or fluctuations, a little bit harder to get a handle on, but nonetheless, you can understand their noise spectrum. There are things that are not Markovian, which we're really trying to now understand a little bit better.
yeah.
So, Akil, did you have a question? I think you turned on your camera.
Yeah. So I guess I didn't really catch this, but what error metrics do you use in this compiler, and how detailed are they?
Well, it depends. So the simple example I gave you, it really just cares, you know, some metric of what's the quality of a qubit, in this case, just using T1 time, and then some metric of what's the quality of a link, you know, and it's just looking at, you know, a C0 error, like fidelity between them. That's just for mapping of our programs. And that, I would say that was like the very first study we did in 2019. But now, you know, we're interested in, you know, all kinds of things, right? So we have techniques to try to mitigate phase accumulation errors. So we have techniques to, you know, try to mitigate amplitude errors. And so, I don't know, I guess we're interested in as much detail as you can give us, actually, right? Because then we can design, you know, specific transformations to our circuits that will help mitigate that noise on a sort of per qubit, per coupler basis.
So, and so you speak of infidelities, this is just randomized benchmarking infidelities?
Yes, I mean, generally we're using randomized benchmarking, but sometimes we find that's not sufficient for what we want to do. And then, but then it's difficult to figure out, you know, how we're going to reliably characterize what's happening.
Yeah, so I think one of the things Irfan was getting at was we've been using methods of just measuring kind of detailed error reconstruction of any parallel gate cycle, and so if you know what C0s are included in a circuit, or what parallel gates are included in a circuit, and you run this kind of error reconstruction, you have detailed information about the Pauli errors of any parallel gate cycle. And so I'm wondering how adaptable your technique might be to this kind of detailed information of what goes on.
Yeah, I guess so one of the so that the first, you know, maybe the second thing I talked about was, you know, given that you if you have a well-characterized system, we can run, you know, some optimizer like Grape to find pulses that give us the best fidelity. If we want to do a whole bunch, like 2 gates in parallel, right, for example. So that would be a situation where that detailed characterization, I think, would be useful. You know, right now, I would say most of our other work deals with it at a more coarse grain level, right? For example, if you have 2 qubits or two 2-qubit gates in parallel that are behaving badly, we just move them apart and not do them in parallel, right? And in a lot of systems, right, the gate error rate is much more dominant than the decoherence that you would suffer by moving those, like, serializing a few things. And so the work that Princeton did with IBM recently on Crosstalk, they basically just serialized every bad pair of things to get better crosstalk behavior. And that's in addition to the fact that IBM already depopulated their machine to get better crosstalk machine, like removed couplers, right? So so that's and sort of the same thing with this you know, this last crosstalk thing that I talked about, right? We're just trying to engineer the system so that frequencies will be far apart and that you won't get any dominant crosstalk effects. Of course, once we do that, then the less dominant effects will begin to matter also. But yeah, but we're very interested in what you mentioned, just because we really understand machines better.
Alexei Morval?
Yeah, I have another question on the first topic that you talk about, like the measurement. I didn't get, like, what was the difference between what you did and what like the usual way. Like when you say, like, we can bunch those measurements, and
Yeah.
like reduce the number of measurements. I didn't quite catch like what's the trick that you like. What was the thing that was making this possible?
Yes. Yes. So I guess the transformation is you can find terms that commute, then you can transform the measurement into a different basis that measures all of those terms simultaneously. And then you have to do some post-processing to separate them out again. But basically,
So
you invest extra gates to reduce the number of measurements.
But if you do that, you probably like, oh, I see. So basically you are saying that at the end, you do something like a transformation and then like one is put to identity and the other to Z, because this is where you can measure the most of the three. And so this way, okay, so okay, I got it.
Right. And then what was interesting was that sometimes even when you do that, you get more error because, you know, sometimes redundancy is good in the measurements. And then, so that there was this covariance thing that we had to do to sort of maximize what we get with the small number of measurements that we take.
Yeah, because, okay. No, that does make sense. Thank you.
Okay, very good. Jean-Luc, do you have a question? You've opened your camera.
And it was, but so this is the graph you showed with all the 2-qubit polys and all the connections, right?
That's right. That's right.
Okay, yeah. We were wondering what was this. So it's just you found that if you all the ones which commute, you can measure them with less turning of the last gates, right? You can do a simple topography. And then the paper, when you separate the green and the yellow, it's 4 qubits, right?
I think so. In the example, you mean?
Yeah, we were looking quickly at the paper, but yeah, maybe so. What's happening then when you separate them in two?
Yeah, and then that's two. That each group is a measurement.
Oh, okay, so you reduce.
It's like two measurements, right? So that the blue and the red are that each one of those groups can be one measurement.
All right. Yeah. Okay. And you are doing this on 4 qubits. Okay, I see.
Yeah.
So maybe I can ask one small follow-up question as well, Fred. This business of crosstalk is quite interesting, right? So one can go ahead and then just sort of say, I'm not going to run a gate or a pair of C-naughts on some particular fiducial set, which has lower fidelity or what have you. Right. With the scrambling work we've done on Qtrits, it was interesting to actually use the always-on dipolar interaction as part of a different gate that you compile. So, and I think this is starting to become popular in some, at least in some high energy physics experiments, where one thinks about this flow K-gate engineering, where you have 2-qubit gates and then interleave with some other rotations to actually go ahead and realize a more complex gate. So is there a way that one could use these crosstalk data that one gathers and use that to sort of recompile the gate set that you want to run? So this is not exactly a grape or gradient descent optimization in the pulse shape, but it says if you have a different interaction, can you renormalize that somehow on the fly?
Yeah, I mean, it's, I don't know. It's not really in our current framework, but it sounds interesting, right? I think that, so what do you mean? So you're saying that we want to sort of renormalize given that we have this extra interaction?
That's right. So in fact, one says that I want a perfect interaction of some textbook fashion, right? And I'm going to call that a gate. I have a different interaction because it has crosstalk. So, but nonetheless, it's two quantum systems that are interacting. And if one can use that to sort of figure out a more appropriate gate sequence and sort of also correct for, and if it's perturbative, you can correct for small imperfections that come in, right? If it's very large, then you may not be able to sort of come up with the right flavor of interaction.
Yeah, I think that's doable. I think that's not dissimilar to other things we try to do with, with noise or even trying to compile using, imperfect gates or things like that.
This is all in the spirit of trying to bring that little crescent that you showed, where the algorithms get closer and the hardware doesn't need to get better. So from an experimentalist point of view, it's much better to bring that crescent closer.
Absolutely, absolutely. Yeah, so I think that could be very interesting what you suggest.
So perhaps we can discuss more offline.
Yeah, absolutely. I mean, for us, it's really, we need an experimentalist to come to us and say, look, this is something that is, is happening that, and if we adjust for that, that will make things easier for us, right? And so that's actually many of the things I talked about, that's how they started, right? So like Dave Schuster or Ken Brown will come to me and say, this is what happens on our machines. I think we can do this. How would we do it? And okay. And so that's a great interaction. We love it.
Okay, sounds good. We're running late here, but any final very quick questions for our speaker before we let him go? All right, let's thank Fred again for a great talk and hope to catch up again soon.
Yeah, thanks for hosting me. I look forward to talking.
Absolutely.